let P be the plaintext, C the ciphertext, and K the secret key in a one-time pad, right? So then we have the following. If each K, so if the key is chosen uniformly at random from all possible keys, and the key is used only once, then you can show that the one-time pad is perfectly secure. So it provides perfect secrecy. And what do we mean by perfect secrecy? We mean the following notion, that the probability that the plaintext is any particular plaintext, given that you observe any particular ciphertext, is just the probability that it was the plaintext without you have observing the ciphertext. In words, this means that knowing the ciphertext gives you no extra information about the plaintext, right? So the ciphertext and the plaintext are just completely independent. So if you think about that, what that means is that when the adversary intercepts the ciphertext, what he is looking at is completely independent from what is being sent, right? In other words, also, what that means is that every plaintext of the same length will be equally likely from the point of view of the adversary, regardless of the ciphertext that he observes. So let's actually prove this, and we'll prove the version for a 1-bit message, right? Now, of course, if you think about communications and so on, everything you can just write in bits, and if you can secure any 1 bit, you can secure a message of any length here. So let's consider that your plaintext is either a 0 or a 1, and that it follows some distribution, but the result is true for any distribution. So there's such a thing as the probability that the plaintext is equal to 1, and there's such a thing as the probability that the plaintext is equal to 0. Okay, so now how does encryption work? So how does the one-time pad encryption work? Well, the way that it works is you generate some secret key in 0, 1 uniformly at random, so uniform and random, and independent from anything else that exists in the world, right? So in other words, probability here that K is equal to 0 is going to be the same as the probability that K is equal to 1, which will be half. And then what you do is your ciphertext is just going to be your plaintext plus your key mod 2. So you're adding in Z2, right? So 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 1 is 0. And so now what we need to show again that the probability, so to prove perfect secrecy, we need to show that the probability that the plaintext is any particular value, given that the ciphertext is any particular ciphertext, is equal to the probability that the plaintext is that value without the observation of the ciphertext. And we need this for every P and C. So let me put a little bar under for the little p, for the small p. So for every P and C in 0, 1. So for every possibility of a bit being sent, we're saying that observing the ciphertext doesn't tell us anything about the plaintext that we didn't know already before. Okay. So let's compute the conditional probability then. So let's do a case, and the other case will be the same. So let's see how we compute something like that. So let's consider that the the ciphertext that was observed is 0. So let's consider the adversary saw that, oh, the ciphertext is the ciphertext 0. Okay. So now, what is the probability from the adversary's point of view that the plaintext was the message 0, right? So that is given that the ciphertext was the message 0. Well, here we can use Bayes' theorem, and so we can write this as the probability that the ciphertext is 0 given that the plaintext is 0 times the probability that the plaintext is 0 divided by the probability that the ciphertext is 0. And now we need to evaluate each one of these. So the probability that the ciphertext is 0 given that the plaintext is 0. So since the ciphertext we saw is the plaintext plus the key mod 2, if the plaintext is 0, then the only way for the ciphertext to be 0 is for the key to be 0. So this is the same as the probability that the key is equal to 0. And the key is uniform random, so this is just half. Similarly, you can also compute the probability that the ciphertext is equal to 0 given that the plaintext was 1. So now, if the ciphertext is 0, the only way for this to happen if the plaintext is 1 is if the key is equal to 1. So the probability of the key equal to 1. And since the key is uniform, this will be half. And with these two, so we can compute this part, and to compute this, we just need to break that expression up by the law of total probability. So probability that the ciphertext is 0 is going to be equal to the probability that the ciphertext is 0 given that the plaintext is 0 times the probability that the plaintext is 0 plus the probability that the ciphertext is 0 given that the plaintext is 1 by the probability that the plaintext is 1. And so this part we just saw, so this is half times the probability that the plaintext is equal to 0 plus the probability that the ciphertext is equal to 0 given the plaintext equal to 1. We just computed it. It's half times the probability that the plaintext is equal to 1. And so this is just half times probability plaintext equal to 0 plus probability of plaintext equal to 1 if you factor out the half. And of course, what's the probability that the plaintext is equal to 0 plus the probability that the plaintext equal to 1? It's going to be equal to 1 because the plaintext has to either be 0 or 1. So this is just by the definition of probabilities. The sum of these has to be equal to 1. So that means that this is equal to half. So with this, we have all the parts that we need. So it'll be half on top times probability of p equal to 0 divided by half. And so this will just be equal to the probability of p equal to 0, right? And let's separate this here. So that means that the probability that the plaintext is 0 given that the ciphertext is 0 is the same as the probability that the plaintext is 0. And you can go and compute the same thing for the probability that the plaintext is 1 and so on. And so you're able to show this definition here, or what we said here, our goal to show this for all the cases. So this means that the one-time pad is perfectly secure.